Torsion is another possibility in which our beams may get failed. Okay, so let's see what is torsion and how this torsion is actually influencing our beam, and how can we make sure that our beam will be safe once we are designing that against torsion. I hope you are able to see the slide, right?
Yes, sir.
So basically, let's see what is torsion actually. We have already seen bending moment, and we have performed the design to ensure that our beam will be safe in bending moment. So what is the main difference between this torsion and bending moment? What is the difference? So basically, if you observe this figure, you have two beams. One is moving in this direction and another one is moving in a perpendicular direction. Suppose you are up, say, let us assume that this is a cantilever beam, and let's assume that you are just applying one point load at this free end. Okay, so if you consider the effect or the rotational effect of this force in this beam, so basically it will be having a rotational effect like this, and it will try to bend in the upward direction, right? So that is actually the effect of bending moment. But at the same time, if you are seeing the effect of bending effect of this load in this beam, what you can observe is that, say if you observe this figure, actually this is trying to rotate in a different manner. That is based on this Z axis, this section, the section cross section of this beam is actually rotated, or it is just twisting this beam which is going in this direction. Okay, this is actually called as torsion. Torsion is basically twisting, whereas in bending moment actually bends the beam. Okay, this is torsion will just try to twist the section. Okay, as you can see in this figure, this section, this highlighted section is actually getting twisted due to the effect of this torsional moment. Acting this torsional moment is actually trying to twist this section. Similarly, if you observe this case here, we have a cantilevered slab here, maybe part of a balcony, and we have a beam which is holding this slab. So basically, when we apply some load on this slab, what will happen? This slab will have a tendency to bend like this, and this action will actually produce a twisting effect on the beam which is supporting this slab. So in such cases, so first thing is that as a designer, you have to look into the cases, and you have to decide whether the effect of torsion is significant or not. If you feel that the effect of torsion is significant, you have to perform the design for torsion also. In some cases, the effect of torsion may be negligible. So in such cases, you can design it as an ordinary beam without the effect of torsion. So first thing is that you have to apply your common sense, and you have to find out whether we should include torsional effect or not. So in these type of cases, we have to actually consider the torsion, because this will be very significant effect produced. There will be very significant effect produced by this torsion in this beam as well as in this beam. Okay, so in such cases, we have to actually include the design for torsions. Again coming to this, so once you are just twisting it, what will happen is that something like your bath towel, once your towel is having some water, what you usually do is that you will just twist it. So once you twist your towel, what you can see is that it will be having some layers like this. As I have drawn on this beam, you can see that some cracks are actually going like this, right? Same pattern will be there in your bath towel also. I hope you have observed that. So basically what I just want to tell you is that once a beam is actually subjected to torsion, the formation of crack will be like this. It will be again almost at an angle of 45 degrees as shown in this figure. Normally this angle will be approximately 45 degrees. But this thing, that is cracks are actually formed at 45 degrees, approximately 45 degrees. We have seen it somewhere else. Where was it? Do you remember? Please tell me. Say at the initial stage itself, I have told you that as a good engineer, once you are observing a failure in a structure, you have to analyze and tell what type of failure it is, whether it is caused by flexure, whether it is caused by shear, whether it is by torsion or temperature or whatever it may be. You must be able to tell that. And one of the simple tool that you can use for this is the pattern of your cracks. And I hope I have already explained the pattern of flexural cracks and shear cracks. And right now my question is, Somewhere else we have already discussed that if the pattern of the crack is about approximately 45 degrees, it is a particular type of crack, or these cracks are actually formed by dash action. What was that?
Shear.
It is basically due to the shear. Okay, so for torsion also we will be observing similar patterns. Say if you observe this from this side, you can see that it is again acting at an angle of 45 degrees. On top side also it is at an angle of 45 degrees. This is the major difference. When a beam is actually failing in torsion, you will observe cracks approximately inclined at 45 degrees on all the sides of your beam. Okay, so because this is completely twisting, this torsion is actually completely twisting the section, so that you will be having cracks all over the section, all over around the section you will be observing these type of cracks. So suppose you are going to a field and you are seeing that one beam is actually failed, it is cracked, and you are observing 45-degree cracks throughout on all sides of the beam. So you can just conclude that there is effect of torsion. That might be a combined effect of shear, torsion, and other things, but there is an effect of torsion because you are observing cracks on all sides of your beam. Okay, so you must be able to observe like that, and please understand that the cracks due to torsion will be always inclined at approximately 45 degrees, and cracks will be formed on all the sides of your beam. So now the next question is how to prevent this. So basically these cracks are actually formed, say once you observe this crack, this is mainly once the crack will be actually formed when you have force acting in the perpendicular direction. Tensile force must be applied in the perpendicular direction so that the weak section will fail and it will get opened. That is what we call as a crack. So once you have a section like this and I am applying a tension in this direction as well as in this direction, and suppose this section is weak, what will happen? This will get separated because this is under the action of tension. So that is what we call as crack. So here we have observed some cracks, and these cracks are approximately at an angle of 45 degrees and on the surface of your beam. So how to prevent that? Or what is your suggestion to prevent it? No suggestion. Just make a try. Let it be wrong or right. That doesn't matter. What is your suggestion? How to prevent these cracks? You have already seen how to prevent shear cracks, right? That was on one of the surface, and again similar to this, you were having cracks at 45 degrees, and yes.
Stirrups
Stirrups is enough. Yeah, right. Very good. Then anything else? So basically, we can use the reinforcement so that that reinforcement must be capable of reducing the effect of this tension. That's all, which is causing these cracks. So in the case of shear, you have already seen that once you have cracks like this, if you are providing vertical reinforcement, it will be effective in preventing this. It will help in reducing the shear, and again it will reduce the tension effect on the concrete, and it will prevent the formation of cracks at inclined direction. Similarly, once you are providing the stirrups, please refer this diagram. Say, please assume that these arrow marks or this red line is actually your stirrups. Okay, so once you are providing stirrups like this, if you observe this side, once these cracks are trying to form, what will happen? We have vertical reinforcement. This vertical side will actually prevent the formation of this crack. And this for the same stirrups, if you observe the top face, what will happen is that once these cracks are trying to form, what will these stirrups do? It will actually prevent this. As you can see in this figure, it will be actually going at an inclined direction against this crack, so that this crack formation will be prevented. So basically this crack will form. Please visualize it in mind. When these cracks are actually formed, when first of all we will be applying some load so that stresses will be developed throughout this beam, and this stress will be acting on the concrete member. And please do remember, concrete member is actually having some capacity to take up the tension. So the concrete will try its maximum to take up these loads, and these loads go on increasing, and at one stage what will happen is that this concrete will fail to take up the tension, so that the crack will be formed. So in such a case, if you have a reinforcement passing against in the required direction, what will happen is that initially the concrete will try to take this tension at the maximum, but at the maximum stage, what will happen is that the concrete will tell steel that, see, I failed, I have done my part, now it is your turn. So once that part or that value is exceeded, this steel will come into picture and it will take up the additional tension so that it will be safe. This crack formation can be prevented. So that is how actually these reinforcements and the concrete are playing their roles. Okay, please understand that. So this is how you can prevent that. So basically, only thing that we require is that we need to provide stirrups throughout the beam, and it must be closed loops. It must not be open loops. So you might have observed that. So what is the time now? Okay, we have 5 more minutes. Say you might have observed that whenever we draw a stirrups, actually it is just necessary to bend this, and after coming to this point, why cannot we just stop it here? In most of the diagrams, you might have seen that this end will be taken like this, and this end will come and it will be taken like this. What is the necessity for this thing? What is the need for that? Say if you are keeping your stirrups like this, say like this, what will happen is that once your beam is getting twisted, this thing will have a tendency to get opened. Okay, this thing will be having a tendency to get opened, because under the torsion, what will happen is that this shear stirrups will get opened, and it will, once it is open, what will happen? Once we have a stress here and this part is actually trying to move, this steel will be in very good bond with the surrounding concrete, so it will just simply move like that. Right? If you are keeping a pen on a surface, just pushing it, it will simply move. Instead, if you are holding at one end firmly and just pushing it, what will happen? It will stay there. So similarly, when this beam is actually subjected to torsion, we need to tie this up. Otherwise, this will simply move. It will not take any load. So for that, what we do is that we will just lock it here. We will just make a loop and close it by forming hoops like this. Okay, and we will put concrete around this thing, and inside also there will be concrete, so it will be firmly locked. So once you have a twisting force, this steel will actually take up the stresses. Is these things clear? Any doubts or anyone?
Sir,
yes.
Sir, we shear reinforcement stirrups in the forms
shear reinforcement stirrups
stirrups shear reinforcement module stirrups vertical stirrups inclined stirrups
if you are designing for shear alone, you have the option to provide either as a loop or as open links also. Say some cases what we will do is that, so please see this figure. Say once we have a cross section like this, and we have our main reinforcement running like this, and stirrups always like this, we have the option to provide it like this, in this way. If you are designing only for shear, you can provide it like this, or in some cases what will happen is that you may be having a number of reinforcement like this. So sometimes we will provide links. Links are actually single thing like this. It will be a single bar which is bent like this. I am just explaining in terms of cross section of the beam. Okay, so sometimes we have the opportunity or option to provide like this or this way or some other way. It doesn't matter if you are simply designing for shear, but once you are, and also in the case of closed loops also, it is not necessary to provide the locked loops if you are just designing it for shear. It will be able to take up the shear, but when the picture of torsion comes, things will change. You cannot provide this way or this way. You have to actually provide it by locking it like this, by providing hooks at required angle. You have to provide the stirrups. Is it clear?
Yes,
the main thing is that we should be able to prevent the opening of the stirrups when it is subjected to twisting. So the twisting actually comes into picture when we have torsion. So in the case of torsion, we cannot just provide open loops. We have to provide it as closed loops. That's it. Okay. Now, any more doubts for anyone up to this point? It's clear. Okay. So, and for the design of torsion, there is no difference, the very slight difference only, but the procedure remains entirely same as what we have done for the design of simply supported beam or cantilever beam. But only difference is that For the design of simply supported beam as well as cantilever beam, we have to perform limit state of collapse in flexure, limit state of collapse in shear. So in both these cases, we require a factored moment as well as a factored shear force, right? So this will be normally calculated based on the action of loads or based on 875, right? But when you design that for torsion, you have to use another shear force and another bending moment. So basically for that, in your IS 46, they have given an equation and called that as equivalent shear force. Equivalent shear for torsion, which is given in clause number 41.3. And the equation for calculating this value, equivalent shear force, is your actual factored shear force at the considered section plus 1.6 times TU divided by B, where this T is your factored torsional moment. Okay, TU is your factored torsional moment. And please note this VU is the VU which you have already used for your design. So basically what you are doing is that you are actually increasing the value of shear force and bending moment acting at the corresponding section and using the same procedure for design, so that it will automatically take care of the torsion. And we have seen that to prevent the crack formation due to torsion, we need only stirrups, and also the longitudinal reinforcement will be also playing a small role in preventing that cracks. And in the case of ordinary beam also, we have seen that while designing for shear, right? So similarly, when you perform the design, please keep in mind, only difference is that you have to use equivalent shear force and equivalent bending moment. Equivalent bending moment, ME1, is given by this expression, that is the normal factored bending moment plus the torsional bending moment. Bending moment in terms of your torsion, that can be again calculated using this equation. MT is equal to torsional bending moment into 1 plus total overall depth divided by your width divided by 1.7. Okay, this is the only difference. So you have to use this shear force and the bending moment for design of your beam. So let's continue what we were learning in the last class. So in the last lecture, we were dealing with limit state of design for torsion, and basically we have seen that in order to ensure safety against torsion, what we have to do is that we have to actually use an equivalent shear force and bending moment, and we have to perform the normal design. This equivalent shear force and bending moment will be a higher value, which will take care of the additional stresses that will be induced in the beam. Okay, so we have seen different clauses for that. So reinforcement, say, as we mentioned, reinforcement are not separately designed for torsion, and the longitudinal and transverse reinforcement, that is your main reinforcement, as well as your stirrups, are designed based on modified bending moment and shear. And in order to calculate this modified bending moment and shear, we have some equations suggested by IS 46 2000, and equations are as shown in this slide, and it is also given in your code. So let's see the clauses corresponding to that. So it is actually given in clause number 41.3 of your IS 46. I hope I am audible and you can see my screen, right?
Yes, sir.
Yeah. So our clause number was 41.3 and 41.4. Okay, so if you come to 41.3, it is shear and torsion, and in the first sub clause, that is 41.3.1, you can see that is given as equivalent shear. So this is the equation which we use for calculating the equivalent shear for performing the design for torsion. So equivalent shear, VE shall be calculated from the formula VE is equal to VU plus 1.6 into TU by B, where each terms are defined here. VE is your equivalent shear, VU is your shear force, that is at the respective section where you are dealing with the design. Then TU is the torsional moment, that sometimes directly torsional moment will be given in the question. Sometimes you will be provided with a load so that you can calculate the moment produced, torsion produced by that load. Okay, the question may be like that. And please note, for torsional moment also, you have to use the factor of safety and convert that to design load. Please note that whenever the working torsional moment is given, you have to convert that into a factored shear, factored torsional moment or design torsional moment. And B is your breadth of beam. Then what else is given here? The equivalent nominal shear stress tau VE in this case shall be calculated as given in 40.1 except for substituting VU by VE. That is the same thing what we have done for calculation of shear. Only thing is that instead of VU, there we have used tau V is equal to VU by VD. But instead of that, here we have to substitute VE by VD. That's the only difference, and VE should be calculated like this. That is the normal shear force plus 1.6 times TU by B. The value of tau V shall not exceed the value of tau C max given in the other things remain the same, exactly same. There is no difference. Now we have next clause. If the equivalent nominal shear stress tau VE does not exceed tau C given in table 19, minimum shear reinforcement shall be provided. That is same thing what we were doing. And if tau VE exceeds tau C given in table 19, both longitudinal and transverse reinforcement shall be provided in accordance with 41.4. So let's see what is there in 41.4. So basically, when you have this effect of torsion, what first thing that you have to do is that you have to check whether torsional reinforcement are needed or not. Say, please see this clause. If tau VE exceeds tau C given in table 19, both longitudinal and transverse reinforcement shall be provided in accordance with this one. Okay, that is what they are mentioning. So when we design for torsion, actually, first of all, you can check whether torsional reinforcement, say longitudinal reinforcement, also must or must not be designed for torsion. How you can provide that? Means how you can check that? So basically, what you have to do is that you have to calculate tau VE based on this thing, that is VE. And if tau VE exceeds tau C given in table 19, we have to design torsion, means provide design for torsion with respect to longitudinal as well as transverse reinforcement. Else, if tau VE is less than tau C, what you can do is that you just provide shear reinforcement in terms of VE, and you can provide your longitudinal, that is flexural reinforcement, in the usual manner. Okay. So that's it regarding that. Now we will move on to this case. Once tau VE exceeds tau C, what we have to do? So reinforcement in member subjected to torsion. So reinforcement for torsion when required shall consist of longitudinal and transverse reinforcement. So longitudinal reinforcement, how to design longitudinal reinforcement? Longitudinal reinforcement shall be designed to resist an equivalent bending moment. These things we have already seen. We will be, in the normal case, we will be designing just for MU, but in order to include the effect of torsion, we have to calculate an equivalent bending moment, which is given by MU plus MT. Okay, and what is MT? MT can be calculated using this equation, which take care of the torsional moment also. Therefore, MT is equal to torsional moment TU into 1 plus overall depth by width of the beam by 1.7. So this is the equation that gives the value of MT. Okay. And one more thing is mentioned here, where TU is the torsional moment, D is the overall depth of the beam, and B is the breadth of the beam. Okay. Now in the next clause, it is mentioned that if the numerical value of MT, that is the additional moment which will take, that we have already seen here, MT, that is equal to TU into 1 plus D by B by 1.7. If that value, the numerical value of MT as defined in that clause, exceeds the numerical value of MU, if that value is larger than MU, what we have to do? This is another case where another check you have to perform. If the numerical value of MT, that is the value which take care of the torsion, exceeds the numerical value of MU, that is the actual moment that is acting at that corresponding section, what we have to do? Longitudinal reinforcement shall be provided on the flexural compression phase also. Okay, so you have to provide reinforcement on compression phase if the value of MT is greater than the actual bending moment that is coming at the respective section. Okay, so shall be provided on the flexural compression phase such that the beam can also withstand an equivalent ME2 given by ME2 is equal to MT minus MU. That is basically the thing is like this. If the value of MT is larger than MU, that is the moment due to torsion, the MT value, not the TU, if MT is larger than the actual bending moment acting at the respective section, what we have to do is that we have to provide some reinforcement on the compression phase also. And in order to design that reinforcement, we require some moment. Basically, these reinforcements, longitudinal reinforcements, are provided to take up the flexural bending moment, right? So for that, which moment should be considered? For that, what you have to do is that you have to take the difference between MT and MU. That is, suppose MU value was 50 kilonewton meter and you obtained MT as 75 kilonewton meter. Then what you have to do is that you have to actually design the longitudinal reinforcement at the tension phase by considering MU plus MT. That is 50 plus this 75. Okay, then what you have to do is that you have to, in addition to that, what you have to do is that you have to provide some reinforcement on the compression phase also. For that, the moment should be the difference of MT and MU. So in this case, it will be 75 minus 50. That is 25 kilonewton meters. For that 25 kilonewton meters, you have to design reinforcement in the compression phase also. And such that the beam can also extend an equivalent ME2 given by ME2 is equal to MT minus MU, the moment ME2 being taken as acting in the opposite sense to that of MU. And that is regarding the longitudinal reinforcement. Now moving towards the transverse reinforcement case. Say two-legged, so please, this is another difference from what we usually do in the case of shear when we design for transverse reinforcement. We will just check the values, that is tau VE with the tau C and tau C max, and after that we will finalize whether we should provide shear reinforcement or not. Then when providing the reinforcement, finally we have to calculate the spacing. So for that we were having some equations, but in the case of torsional design, we need to use these two equations. Okay, so let's see what these equations say. See, two-legged closed hoops enclosing the corner longitudinal bars shall have an area of cross-section ASV given by ASV is equal to, we have two equations for calculating ASV. Okay, and you have to calculate the value of ASV using both these equations. And finally, what we have to do is that here one clause is given, but the total transverse reinforcement shall not be less than this value. Okay, so finally what you have to do is that you have to provide ASV which is larger. Say you will calculate ASV from this equation and this equation, and finally you will have to provide the larger quantity. Suppose from this equation I am obtaining it as say 200 millimeter square, and from this I am obtaining it as 250 millimeter square. So I have to provide 250 millimeter square. So based on that, we have to actually provide the spacing, or normally in the case of shear reinforcement, we will be fixing the diameter and finally we will be varying the spacing. So based on that value, you have to provide the spacing. So those are the things regarding the torsional design. Do you have any doubts in this, the procedure?
Sir, MT greater than MU വരുന്ന കേസില്ലേ? അപ്പൊ അതിന്റെ MT മൈനസ് MU എന്നുള്ള ഡിഫറൻസ് നമ്മൾ MUലേക്ക് ആഡ് ചെയ്തിട്ട് അതിന് വേണ്ടിയാണ് ലോഞ്ചിറ്റ്യൂഡിനൽ ഡിസൈൻ ചെയ്യണേ?
അതെ, ഡിഫറൻസ് ആഡ് ചെയ്തിട്ടല്ല. ഫസ്റ്റ് ഓഫ് ഓൾ we have to say, as the example which I have mentioned, if MU is 50 and MT is 75, we have to take 75 plus 50 and design reinforcement in the tension zone. In addition to this, we have to take the difference between MU and MT, that is 25, and before this 25 we have to provide some reinforcement in the compression zone also.
Okay sir, okay.
Any more doubts? So in that case we will proceed with the problem, so that if you have any minor doubts at any stage, that will be clear while doing the problem. Okay, so you can note it down. So this is the problem. Okay, so let's see, as this is the first problem, so let's see what are the different steps we have to do. So basically first of all, what we are doing is that we are just calculating the equivalent shear, and we have to check whether we have to perform the flexural design also in terms of by considering torsion or not. So for that, in the first stage, what we will do is that equivalent shear, we will calculate the equivalent shear. So in this case, total depth D is equal to 550 millimeters, that is given in the question. Assume 20 millimeter diameter bars and 25 millimeter nominal cover and 10 mm diameter stirrups. These are some assumptions made. So basically, we can, from these assumptions, we can calculate the value of effective depth small d as overall depth minus the cover minus the diameter of stirrups, then minus the half the diameter of main bars. Okay, So that will give you around 505. Let's take that. That is around 505. Now what we have to do is that we have to calculate the equivalent shear force, which is given by VE is equal to VU plus 1.6 tau U TU by B. Okay, that is equal to, again, the VU is given in the question, right? Factored shear force is given. So basically, and the TU is also given. So we are just directly substituting the value 70 plus 1.6 into 40 by 0.3, which will come around 283.333 kilonewtons. And so now we will calculate the value of tau VE. Tau VE is equal to 283.333 into 1000 by 300 into 505. That is B into D. So basically, here we have VE divided by V into D, and I have just converted that into Newton. So I am obtaining a value of 1.87 Newton per millimeter square. Now from table 36.2, tau C max is equal to 2.5 Newton per millimeter square. Hence, so this tau VE value is actually less than, this is 1.87, and this value is 2.5. So basically it doesn't exceeds the value of tau C max. So we are proceeding with the design. So now what we have to do is that we have to calculate the equivalent bending moment also, and that value is actually given by ME1 is equal to MU plus MT. Therefore MT is equal to, we have the equation, and substituting the given values in the equation, what we get is MT is equal to 66.67 kilonewton meters. Now the equivalent moment is given by MU plus MT. So basically this is your factored moment and this is your MT value, and adding up we will get it as 146.67 kilonewton meters. Now as per our normal design, what we can do is that we will just use the equation corresponding to balance section. Therefore the moment of resistance of a balance section is given by MU limit is equal to 0.36 FCK XU max by D into this equation. You already know that. And we are using FE for 415. So corresponding X limit by D value should be taken. You can take it as either 0.48 or the exact value. Okay. Now substitute it here and calculate the moment carrying capacity of a balance section. That is the maximum permitted value for your section. So in this case, MU limit is coming around 158.56 into 10 raised to 6. Now what we have to do is that we have to compare these two values. Then only we can decide whether we should provide reinforcement in the compression side or not. So when you compare that, our ME1 value was 146.67 and MU limit value is 158.56. Therefore ME1 is actually in this case less than MU. Okay, so basically we need not provide reinforcement in the compression side. So if the case was different, if ME1 was greater than MU limit, what we have to do is that we have to actually provide some reinforcement in the compression side also. Okay, now MU is equal to, so basically now we are going to design the reinforcement at the tension phase. So we are using this ME1, M effective, because we are considering the torsion also in this case. So ME1 is equal to 0.87. We are designing it as a this under reinforced section. So ME1 is equal to 0.87 Fy AST D into 1 minus. Why I have used this under reinforced equation corresponding to under reinforced section? What can be the reason for this? If you not here, our
limiting
MU,
yes,
ME is less than MU limit.
exactly correct. So basically the maximum capacity of our section will be that of a balance section, that up to that point we can provide. And in this case we have seen that for balance section it will be having a capacity of 158.56 kilonewton meters. Okay, so but we are right now designing for a smaller moment, that is ME1, which is equal to 146.67 kilonewton meters. So basically it will be a section, if you are designing the section to have a capacity like this, which is lower than the capacity of a balance section, it will be automatically a under reinforced section. That is the reason why I am sticking on to this equation. So basically ME1 is equal to 0.87 Fy AST into D into 1 minus Fy by FCK into AST by VD. This is your equation, basic equation. From this you can find the value of your AST. So from here I think there is slight mistakes in the numerical value. So you just don't consider these numerical values. You just do your own calculation and find out the actual AST. So from this the AST which is obtained is, say, something like 1012.02. Okay, so from this we will be getting we will be in need of an AST like this. So hence we will provide 4 bars of 20 millimeter diameter having total AST of 1256. This AST is actually larger than that is required. Again, as MT is less than MU, we need not consider MU2. This thing was already explained. Since this moment was less than the MU value, this value is actually less than the MU limit value. We need not provide design in the compression side. Therefore, provide only bars of 12. Okay, so basically this is regarding the stirrups holders. So you can either provide 10 mm bars or 12 mm bars on compression phase to act as the stirrups holders. Okay, holding bars for transverse reinforcement. That's all. So that will complete our flexural design. After that, what you have to do is that you have to design for transverse reinforcement also. So basically moving on to the design for transverse reinforcement. Now we have completed the flexural reinforcement, and we know that how many reinforcement are there. There are 4 bars of 20 mm diameter which is provided in the flexural side. So based on this AS, we can calculate the value of 100 AS by BD, because in order to calculate the value of tau C, we need this value 100 AS by BD. Then only we will be able to calculate tau C with respect to this 100 AS by BD and the grade of the concrete from the corresponding table. So what you have to do is that you basically calculate the value 100 AS by BD, and then you find the value of tau C corresponding to that. Okay, so in this case tau C will be obtained around 0.52. So once you obtain the value of tau C, as we were doing in the case of design for shear, in the case of ordinary design, what we will do is that we will just compare the value of tau V with respect to tau C and tau C max. So here we don't have tau V, instead we have tau VE, which is a modified value of stress corresponding to that of torsion also, which includes the effect of torsion also, and we have already calculated the value of tau VE in the initial step. So now what we will do is that once we get the value of tau C, we will compare that tau VE with respect to tau C and tau C max, and we will check whether reinforcement should be provided or not. So in this case, we can see that tau VE is actually coming larger than tau C. So basically we have to provide transverse reinforcement, and we are assuming that we are going to provide 2-leg stirrups, and the diameter is assumed to be 10 millimeters. And as per the code, we have 2 equations, and if you remember back in the code, I think it was in page number 74 or something. 70. Yes, here we have instead of torsion. Okay, so basically if you refer clause number 41.4.3, you have some equation: 2-legged close hoops enclosing the corner longitudinal bars shall have an area of cross section. So basically they are providing some restriction on the amount of area that should be provided when we consider the effect of torsion. So for that they have actually provided 2 equations, and we have to actually ensure that the total transverse reinforcement shall not be less than this. So this is the minimum. So first of all, you have to find out the value corresponding from both these equations, and you have to stick on to the larger value. And we have already seen how to calculate the larger value. So this was our basic equation, and we have some put some rearrangement, like it was in terms of say something like ASV into 0.87 Fy by SV, and we obtained some numerical value equivalent to that. Similarly, from second equation also we obtained some value for ASV into 0.87 Fy into SV. So if you remember that this was that. And in the second case, from second equation, this value was corresponding to a numerical value of 387. And in the first case, we obtained it as 527. So if you are taking this spacing to the other side and bringing this value to the denominator, you know that you just want to provide the maximum amount of reinforcement as suggested by both these equations. So once you have a larger value in the denominator, what will happen? This is actually one, you are just taking the spacing to the right hand side and bringing this numerical value to the denominator. So basically here we have the spacing equal to some constant value divided by 527, and in the second case we have spacing equal to again the same constant value divided by 384. So we know that when we have a larger number in the denominator, we will be obtaining a smaller value as our spacing. So as our spacing decreases, what actually happens is that the amount of area of transverse reinforcement is actually increasing. This spacing is actually the center to center distance of your stirrups. So basically when the stirrups are closely spaced, what will happen is that you will be having more number of stirrups and thereby the cross-sectional area will be larger. So basically in this case, when you have 527 in the denominator, you will have a larger quantity. So you have to find out the spacing with respect to this first equation. So we have done that, and we have observed that the spacing required is around 115.79. So we have provided the stirrups at a spacing of 100 millimeters. So if you remember back, when we approximate or when we round this off, we cannot round it up because the minimum spacing required is 115. So that much reinforcement is anyway required to us. So when you are rounding it, what you have to do is that you have to round it down and reduce the spacing. So in this case, what they have done is they have taken the spacing as 100, which is less than the minimum requirement. So it will be safe. We are additionally providing some transverse reinforcement, so it will be safe. So this is how they have provided this. And coming back to this equation, let's go to IS 446. So if you refer this equation, you can see that different terminologies are there. Tau v we have already seen, that is the torsional moment. Then we have SV corresponds to the spacing between the transverse reinforcement. Then we have VU, which is the factored shear force acting at the respective section. Again, we have SV. Then we have another term B1 and D1. What is this B1 and D1? Let's see that. So here the explanation is given like B1 is equal to center to center distance between the corner bars in the direction of the width. Similarly, D1 is equal to center to center distance between the corner bars. So coming back to one of the slide. So basically, if you see this, if you take a cross section, say please look into this slide. So once you have a cross section like this, we should have at least a minimum of 1 bars provided at each of these corners when we take into account the case of torsion. So basically B1 means the center to center distance between these bars. Okay, the distance from the center of the first bar to the center of the second bar is actually termed as your B1. Similarly, the distance from the center of this bar to the center of this bar in the vertical direction is termed as your D1. I hope the concept is clear. It's pretty simple, just the center to center distance between these bars, corner bars. Corner bars means sometimes what will happen is like you will be having more number of bars here. So basically you have to actually take the center to center distance between these corner bars as your B1. Okay, and the distance between the center to center of, say, sometimes you will be again having 2 layers of reinforcement. So in this case, when you take D1, what we have to do is that you have to take the distance from the center of this layer of reinforcement to the center of this layer of reinforcement. That will correspond to your D1. That is what is mentioned in the code. So coming back to the code, so that is regarding B1 and D1. Then we have 0.87 Fi. Fi is your strength of steel. Okay. And coming to the second equation, we have tau VE. This thing we have is already seen, shear stress, which accounts the effect of torsion. Then we have tau C. Tau C is the shear strength, shear capacity of our concrete. Then we have the width of the section. So here we have B. B is the breadth of the member. That is the total width of the member. Then we have SV as well as 0.87 Fi. So these things are familiar to you. So this is the only new thing is B1 and D1. So this is how you calculate the value of B1 and D1. I think the concept is clear. Is it clear? Any doubts in that? Regarding B1 and D1, right?
Yes.
So basically, when you consider a cross section, say you will be considering a section for the design, right? So the thing is how to take the value of B1 and D1. So basically what they mean is, say first thing that you have to understand is that for torsion, when you consider torsion, you should have at least 1 reinforcement in every corner. So basically we will be providing a transverse reinforcement for prevention of torsion, and we will utilize the longitudinal bars. So when we have a transverse reinforcement means it is your stirrups. So in the case of these stirrups, it is enforced that you should have at least 1 reinforcement at every corner. So basically as a minimum, we will be having 4 reinforcements like this. 1 here, 1 at this corner, another one at this corner, and another one at this corner. And around this, we will be having a hoop. That is your stirrups. So basically, in this case, this is the very, very minimum case. In this case, B1 means the distance in the horizontal direction from the center of this left reinforcement to the center of this right reinforcement. So this corresponds to your B1. Similarly, in this particular case, D1 corresponds to the center distance from the center of this bar to the center of this extreme bar. This is your D1. Is this clear to you?
Yes, sir.
Yes. See, in advanced cases, what will happen is that sometimes the beam will be designed to carry a large amount of load. So you may be having some more reinforcement here. So in such case also, the definition of B1 and D1 remains the same. In that case also, you have to take the center to center distance between the reinforcement in the corner portion, extreme reinforcement. So if you consider the left side, this is the reinforcement which is provided at the far end. Similarly, if you consider this reinforcement, it is the reinforcement provided at the far end in the right side. Similarly, in the vertical direction also, this is the reinforcement provided in the far end if you are considering in the upward direction. Similarly, this is the reinforcement provided in the far end if you consider it in the downward direction. So basically, to calculate D1, you have to take the center to center distance between these bars which are kept at the extreme ends. That is regarding B1 and D1. Any more doubts? Is it clear?
Yes, sir.
Okay. So that was regarding these two equations. Now we have one more thing, that is regarding how to provide the reinforcement. So for that, so these things we have already seen, how to calculate the spacing. Now in order to provide, we have some restrictions, say like we have already seen in the case of beam, we can provide a maximum percentage of 4% reinforcement. There was a maximum amount and a minimum amount. Similarly, for other cases also we have seen, in the case of shear also we have seen that we have some minimum suggestion from the code as well as maximum suggestion from the code. So likewise, in the case of torsion also we have some criteria. So let's see that. So these criteria are actually given in your IS for physics, again in clause number 26.5.1.7. So let's move on to our code. And in the initial class, I have just fastly gone through this, and I have mentioned that while discussing torsion, we will come back to this. It was 26.6 point something, right? 26. Okay, so side face reinforcement. So basically, if you remember back, 26.5 was requirement of reinforcement for structural member. These things we have already seen in the case of beams. Regarding tension reinforcement, we have some minimum reinforcement suggested by the code based on this equation. Then we have some maximum reinforcement. Likewise, we have for compression, we have for every case, we have some suggestion from the code. And right now we are dealing with torsion. So we will move on to the corresponding code. See, if you see distribution of torsional reinforcement. Right now we have already designed the longitudinal reinforcement for torsion as well as the transverse reinforcement for torsion by considering the equivalent shear force and equivalent bending moment. Okay, now how to provide this? Is there any restriction? Let's see that. So when a member is designed for torsion, see clause number 41 or B6 as per, because we have already followed the clause or the details given in clause number 41 and perform the design by considering the equivalent shear force and equivalent bending moment. So when a member is designed for torsion as per this clause, reinforcement shall be provided as below. Okay, so let's see what is there. So the transverse reinforcement, that is your stirrups. Transverse reinforcement for torsion shall be rectangular closed stirrups placed perpendicular to the axis of member. So if you remember, when we designed for shear, we were having the freedom to provide it in some angle, or we can provide it as in the vertical direction, or we can even utilize the flexural bars. But here the case is different. The transverse reinforcement for torsion shall be rectangular closed stirrups. So they have specifically mentioned that it should be rectangular closed, again closed. I hope you remember the concept of looping. Closed stirrups, again that is placed perpendicular to the axis of member. So we have some restriction. We have to actually provide that in the vertical direction itself. Axis of the member. The spacing of the stirrups shall not exceed the least of the following. That is, we have three conditions, and the spacing which we are adopting should not be less than this. Okay, let's see what are the conditions. First one is x1. Second one is x1 plus y1 by 4, and then we have 300 millimeters. So we have 3 values, and we have to ensure that the spacing which we have adopted. So for the problem which we are discussing now, we have actually provided 100 mm as the spacing. So it should be compared with these 3 values, and we have to ensure that this 100 is actually larger, smaller than all these values. So it shall not exceed the least of these 3 values. So let's find the least of these 3. First one is x1. What is x1 then? Where x1 and y1 are respectively the shorter and long dimension of the stirrups. So please again note where x1 and y1 are respectively the short and long dimension of the stirrups. So if you go back to your slide where we have discussed about this thing. So I don't. Okay. So we have just now discussed about D1 and D1. X1 and Y1 is again something similar to this. So basically the thing is like how they are defining it is like this. Again we have the same section. It is similar, not equivalent to B1 or D1. And here we will be having say at least 4 reinforcements. Then what we will do is that we will provide our stirrups over this, right? We will be providing it over these reinforcement, and again this will be having some thickness. Okay, and what you have to do is that in this case x1 will be the center to center distance of this one. Say here on the left side you have a thickness which will be equal to the diameter of the stirrups which we have assumed. So in this case we have assumed around 10 millimeter diameter stirrups. So this thickness will be 10. Okay, so I have to take the center point of this one. Similarly on the other side also I will be having a center point. Now this horizontal distance will correspond to your x1. Similarly on the vertical direction I have a thickness here. So I have to mark the center point here, and I have to again mark the center point on bottom, and this vertical distance will mark or will be equal to my y1. So this is how you will calculate the value of x1 and y1. So you have basically your longitudinal reinforcement and your stirrups running around that. It is a loop, closed loop actually provided around the longitudinal reinforcement. So what you have to do is that in order to calculate x1, you have to take the center to center distance like this. Center to center distance in the shorter direction means it is this one, and center to center dimension in the longer direction means it is your y1. Is the concept clear? Any doubts in that? Okay, I assume that you have understood that. So basically these are the equations suggested by the code. So basically we have to calculate the value of x1. In this case x1 is coming around 240, y1 is coming around 490, and the spacing which we have provided is just 100 millimeters. So if you consider or compare it with x1 is 240. So it haven't exceeded our first term, that is x1. Then we need to calculate x1 plus y1 by 4. Which is coming around 182. Again, our 100 mm haven't exceeded this value, and we have a third condition, that was say x1 and x1 plus y1 by 4 is considered. Now we have a third condition of 300 mm. Again, our 100 mm is less than 300 mm, so we are safe. So we can provide that. Okay, that is the reason why in this problem, hence 10 mm diameter 2-leg stirrups are provided at 100 millimeters center to center. Suppose from the design you have provided it at a distance of maybe 250 millimeters. So in the previous step here, suppose I am just not talking about this problem. In some other problem, you obtained the spacing as say 250 millimeters, and when you perform this check, you will find that x1 is 240, but the distance provided is 250, which have exceeded this value. So you cannot provide 250. What you have to do is that you have to restrict that to this value 240. Also compare with the remaining two and ensure that you are providing the smallest of all these values. Okay, so that is how you will complete this problem. And we have one more clause here. Let's firstly go through that. Longitudinal, that this was regarding your transverse reinforcement. And what about longitudinal reinforcement? Let's see that. Longitudinal reinforcement, that is our main reinforcement which we have designed for flexure. Longitudinal reinforcement shall be placed as close as is practicable to the corner of the cross section in all the cases. So it is pretty straightforward. We have to keep the reinforcement towards the end. That means the cover should be as minimum as possible. So longitudinal reinforcement shall be placed as close as in practicable to the corner of the cross section, and in all cases there shall be at least one longitudinal bar in each corner of the ties. As I have already explained, when you include the effect of torsion, it is necessary, it is enforced that we should have at least one reinforcement in every corner. Okay, that is what is mentioned here. So there shall be at least one longitudinal bar in each corner of tie. That may not be the main bar or the compression reinforcement. That can be even the stirrups holders. That is okay, but we should have at least one bar in every corner. That's it. And when the cross-sectional dimension of the member exceeds 450 millimeters, see the depth of the member is exceeding 450 millimeters, what do you have to do? Additional longitudinal bars shall be provided to satisfy the requirement of minimum reinforcement and spacing given in 26.5.1.3. So basically you have to provide additional minimum reinforcement. Along with that, the spacing, there is some more restriction on the spacing which is mentioned in this clause, that is 26.5.1.3. Let's move on to that. 26.5.1.3, that is regarding side face reinforcement. So when this is the case, what happens is that you just visualize the dimension or the depth is larger than 450 millimeters. That means it is almost half a meter. That is, the beam is having a very larger depth. In such a case, what we have to do is that we have to actually provide side face reinforcement. When we consider torsion, the dimension, if the dimension exceeds 450 itself, we have to provide. In normal case, actually, we will be providing the side face reinforcement when this depth is more than 750 millimeters. But when we include the effect of torsion also, if the depth is more than 450 millimeter, we have to actually provide the side face reinforcement. And how to provide that? So where the depth of the web is, this you need not consider, because right now we are dealing with torsion, and from the clause regarding the torsion, they have mentioned that if the depth is more than 450 itself, we have to provide side face reinforcement. Side face reinforcement shall be provided along the two faces. So on both the face where we have the depth, we have to actually provide the side face reinforcement, and the total area of such reinforcement shall not be less than 0.1% of web cross-sectional area. Okay, what do you mean by web cross-sectional area? Do you have any idea regarding web cross-sectional area? No idea. Have you heard the term webs and flanges? I am pretty sure that you have heard about that from mechanics itself, engineering mechanics itself.
Yes, in an I section, like webs and flanges.
So suppose you have an I section. I hope at least you have heard about I sections. So these things corresponds to your flanges, and this is your web. Okay, in the case of rectangular section, you have only web portion. Okay, so basically this will be your web portion. This hatched area is your web portion, and here what they suggest is that the total area of such side face reinforcement shall not be less than 0.1% of your web area. So basically you have to calculate that area, total area, cross-sectional area, and find 0.1% of that, and you have to provide reinforcement at least corresponding to that much area. Okay, suppose the total area is 100, you have to multiply 100 by, or you have to find 0.1% of 100, that is 100 into 0.1 by 100. Okay, that much square area should be additionally provided by taking some diameter bar. It can be 8 mm, 10 mm or something else, and please ensure that you are getting a cross-sectional area of that much, and these bars should be equally distributed on the surface. So when you see from the side, you have to actually equally distribute this reinforcement on the surface. And one more thing is that the spacing should not exceed 300 millimeter or the web thickness, that is B, width of the beam, or 300 millimeter, whichever is less. So basically, yeah.
So 450 mm exceed ചെയ്യുമ്പോഴാണ് നമ്മൾ മറ്റേ ഷിയർ റീഇൻഫോഴ്സ്മെന്റ്സും കൂടി കൊടുക്കേണ്ടി വരുന്നത് ലോഞ്ചിറ്റ്യൂഡിനൽ ബാസിന് വേണ്ടിയുള്ള.
ലോഞ്ചിറ്റ്യൂഡിനൽ ബാർ മനസ്സിലായില്ല എനിക്ക്.
ഇപ്പൊ നമ്മള് ടോർഷന് വേണ്ടി നമ്മൾ ടോർഷന്റെ ഇതും കൂടി ഇൻക്ലൂഡ് ചെയ്തിട്ട് ഷിയർ റീഇൻഫോഴ്സ്മെന്റ് ചെയ്ത് കഴിഞ്ഞാലും നമ്മുടെ ബീമിന്റെ ഡെപ്ത് 450 mm മേലെ ആണെങ്കിൽ നമ്മൾ ആ മിനിമം ഷിയർ റീഇൻഫോഴ്സ്മെന്റ്സും കൂടിയും കൊടുക്കണം.
കൊടുക്കണം, അഡീഷണൽ ആയിട്ട് കൊടുക്കണം. അത് എക്സ്ട്രാ, we have to decide that as an additional reinforcement. Side face reinforcement are normally designed as an extra reinforcement. Was that your doubt?
Yes, sir. Yes.
So this is actually not only applicable in the case of torsion. In the case of normal beams also, we have to provide side face reinforcement. But in that case, we will provide side face reinforcement only in case when the depth is more than 750 mm. In such a case, it is actually a deep beam. It is considered as a deep beam. So that is the reason why we are actually going with this side face reinforcement and all. And the normal case, it won't be there.